Hello, hello, hello. This is Nicholas after a lovely spring break. And I finally have gotten around to do the video on the volume of a hypersphere. So imagine you start with a square and this side length here is 1. And then what you do is you inscribe a circle in the square. So the amount of the so if we were to consider the amount of the area of the square that is also contained in the circle, in other words, this area here. So the area of the square is obviously equal to 1 if the side lengths of 1, and the area of the circle is pi times 1/2 squared, or pi over 4. So then the amount of area occupied by the circle of the total area of 1 of the square is just pi over 4 out of the total of 1, or just pi over 4, which if you plug that into a calculator, you get that approximately 78.5% of the area of the circle covers 78.5% of the square, approximately. Now, let's consider, instead, if we had a cube. I'm not going to draw it because I'm a bad 3D drawer, but let's say we had a cube and a sphere. Now you can imagine what those look like, and the area of the square is, now it's a cube. Whoa. The area of the cube is 1, and the area of the sphere is 4/3 pi times 1/2 cubed. And if we were to find the ratio of the areas, just like how we did up here, we would, let's see, we plug that in to a calculator. And let's see here. We get approximately 52.36% of the area of the sphere, that is also that 52.36% of the area of the cube is contained by the sphere. Okay, now here's my claim, which is a really cool claim, and this is what I'm going to be spending the video proving, because it's just so counterintuitive to me, at least. The claim is that, I'm going to let n throughout the whole video be the number of dimensions. And perhaps it might be a little beneficial to talk about what a dimension actually is. From a mathematical standpoint, a space is said to be n-dimensional if you can create n lines that are all perpendicular to one another. So, for example, if we're in 2 dimensions, we can have this line and then this line, and they can be perpendicular to each other. That's 2-dimensional. Now, this is obviously a 2-dimensional surface I'm drawing on, but you guys can know what 3-dimension looks like. We have a x, we have a y, and we have a z-axis, and those are all perpendicular to each other. And that's what's defining of 3 dimensions, at least from a mathematical standpoint. So n dimensions means n mutually perpendicular lines in the space. So the claim is that as the number of dimensions approaches infinity for the for the cube and the sphere, in other words, we're doing like a tesseract, which is a 4-dimensional cube, and a hypersphere, a 4-dimensional sphere, then the volume that the hypersphere the hypersphere, volume that the hypersphere contains of the hypercube goes to 0. And we're starting to see that here, right? It started out at 78.5%, 52.36%. And as we increase the number of dimensions, we're going to find out it goes to 0. And the way I'm going to approach this is I'm going to derive a formula for the volume of an n-dimensional hypersphere, and then I'm just going to take the limit as n goes to infinity, and it will be clear then that that formula does go to 0 as n goes to infinity. So, lemma number 1. My first claim in the proof is that V sub n of R, in other words, the volume of an n-dimensional sphere with a radius of R, is simply R to the n, the radius to the number of dimensions, times the volume of an n-dimensional unit sphere. So if I can prove this claim, it suffices to just consider unit spheres, unit hyperspheres, because if you just can find the volume of a unit hypersphere, then just multiply by this and you got for any radius. So what am I going to do? Well, I know from multivariable calculus that the volume, in other words, the absolute value of V sub n of R, is nothing but the integral, and it's just 1 dx sub 1 dx sub 2 ... dx sub n. And that gives you volume in the most general case. So this is really n integrals right here. We have an integral of an integral of an integral. We have n integrals here of just 1 dx sub 1 dx sub 2 ... dx sub n. And I'm going to do a nice change of variables here. I'm going to let y sub I be equal to x sub I over r. And so now we need to compute the Jacobian for that change of variables. That's why I did the video on the Jacobian before. So dy sub 1, dy sub 2, dy sub n is, I'm not sure if probably need to move this over. I don't think I have enough room here. So this is nothing but the absolute value of the matrix, partial derivative of y1 with respect to x1, ... partial derivative of y sub n with respect to x1, partial derivative of y1 with respect to xn, and we have a bunch of entries. It's an n by n square matrix, and partial yn with respect to x sub n. Dx sub 1, dx sub 2, dx sub n. And now when we compute these partial derivatives, well, we still have the absolute value, and the matrix will just, okay, let's start from the top here. This partial derivative right here, partial y1 with respect to x1. Okay, so I still have the laser. Y sub 1 is just x sub 1 over r. So when we take that partial derivative, x sub 1 just becomes 1, and 1 over r is a constant. So the partial derivative is just 1 over r. Now, everything else is 0, 0, 0. And we just have 1 over r's along the main diagonal here. And everything else is 0, 0, 0, 0. It's all 0, except for the 1 over r's along this main diagonal here. And there's really n of those 1 over r's in the matrix. So the determinant is we just get 1 over r to the n, dx sub 1, dx sub 2, ... dx sub n. Now, that means that dx sub 1 dot 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 dx sub n is r to the n times dy sub 1 dot 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 dy sub n. Okay, and then that would imply that the absolute value of the volume of an n-dimensional sphere of radius r is the integral over the field of the unit n-dimensional hypersphere of just 1 times our differential, which is r to the n dy sub 1 dot 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 dy sub n. And that is nothing but r to the n, because this is a constant, bring it out front, times, and then the 1 dy sub 1 dy sub n is the volume of an n-dimensional unit sphere. So this implies v sub n of r is r to the n times v sub n of 1. So the lemma 1 is complete. Okay. Now, let's do some disk method here. So let's try to imagine this with me. So we have the origin of our hypersphere, or the center of our hypersphere, and we're assuming it's a unit hypersphere, so it's radius 1. So maybe out to here, this is the radius, and so this radius is 1. This is just call it x sub I guess. It's some length in some coordinate axis direction, and call this length r, which, if this forms a right triangle here, it's a cross section. This r is equal to 1 minus x sub I squared. Or I'll just call it x sub 1 because I use x sub I over there. Okay. So that would mean that we can write that v sub n minus 1 of r is v sub n minus 1 of square root of 1 minus x sub 1 squared. Okay, and if we're considering a unit sphere, then v sub n of 1 is just the integral from -1 to 1, because the bounds are just from where the hypersphere starts and ends, and if it's got a radius of 1, then that is what the bounds are. Of the area of this, the cross-sectional area of each of the one-dimensional less cross-sections. In other words, if we have n-dimensional sphere, it's a cross-section of dimension n minus 1, dx sub 1. Okay. And this area is just as I said before. So we have an integral from -1 to 1, and the area is given by those cross sections, and the formula for each of those is given by the square root here. So, and it's v sub n minus 1 because the cross sections are 1 dimension less than the actual solid itself. So, this is the integral from -1 to 1 of square root 1 minus x sub 1 squared to the n minus 1 times v sub n minus 1 of 1 dx sub 1. So all I did there was just apply the lemma that I established right here. Okay, now that's gonna be Well, v sub n minus 1 of 1 is a constant, so we can pull that out front. And we have an integral from -1 to 1. I don't really like this square root, so I'm going to get rid of that. So that's n minus 1 over 2 because of the 1/2 from the square root. Dx sub 1. And this is a even function, so this is 2v sub n minus 1 of 1s times the integral from 0 to 1 of 1 minus x squared times n, or to the n minus 1 over 2 power dx sub 1. So let's see. What do I want to do? So let's not let's remember what this is all originally equal to here. This is all let me here, hope I got it. I think I got it. Okay. All right. So all of this stuff here is the volume of a unit sphere here. This is the v sub n of 1, a unit hypersphere. So let me move that over. Okay. Now, I think I just want to let... Oh, I don't really like this x squared here, so I'm going to get rid of it. I'm going to let u be equal to x squared, and so du is 2x dx. Okay, so we now get 2v sub n minus 1 of 1 times the integral, and the bounds are still the same from 0 to 1, of 1 minus u to the n minus 1 over 2 times 1 over 2u du. Okay. The 2's will cancel out. That's really nice. Okay. And so now we just have v sub n minus 1 of 1 times the integral from 0 to 1 of 1 minus u to the n minus 1 over 2 times u to the negative 1/2 du. Now, this is where things start to get cool if they haven't gotten cool already. Because, now I didn't really know this at first actually, so this here has a very special name. This is known as the beta function. It's a multivariable integral function, and so it's defined like this. I'll just put it as a note. So beta of x comma y is the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. So it's parameterized in terms of t. And it turns out that this is useful because, well, there's another function. Now, this one is more well known than the beta function, but it turns out that beta of x comma y is gamma of x times gamma of y over gamma of x plus y. That's pretty cool. And gamma of x it analytically continues x minus 1 factorial. So what does that mean? It means that, well, traditionally the function x factorial is defined only for the integers. In other words, it doesn't make sense to ask, for example, what 1/2 factorial is. That doesn't make sense. And in your middle school or maybe high school class, you would have learned that the factorial tells us how many ways we can arrange n objects. Of course, n is a positive, well, it could be 0, a non-negative integer. It's an integer traditionally. But what we can do with this gamma function is it extends the factorial function for all. Well, it extends the factorial function for most real numbers. For example, you can't do -1 factorial with the gamma function. It will break down. But and you can do it for complex numbers too, which is really cool. So it extends the domain of the factorial function to more than just the non-negative integers. And I guess I should probably say what gamma of x is actually defined to be. So gamma of x is the integral from 0 to infinity of e to the minus u times u to the x minus 1 du. And this is the same thing as x minus 1 factorial. And as maybe you'd want to try it out for yourself, if you, say, plug in a gamma of 2, that's the integral from 0 to infinity of e to the minus u times u to the 1 du. And that can be evaluated really easily with integration by parts. And in fact, all of the integer ones can be evaluated really easily with integration by parts. You just you differentiate this until it goes to 0, and you just keep integrating this, and it just changes signs every other. But you'll find that this integral will, in fact, give you 1, which is the same thing as 2 minus 1 factorial, or 1 factorial. 1 factorial is 1. So you can fool around with that for yourself and see. Okay. So let's see what gamma of x times gamma of y gives us. Gamma of x times gamma of y is integral from 0 to infinity e to the minus u to the x minus 1 du times the integral from 0 to infinity of e to the minus u, and let's use a different v to the y minus 1 dv, which is the double integral from 0 infinity of e to the negative u plus v, u to the x minus 1, v to the y minus 1, du dv. And now don't, I have a interesting change of variables here. I honestly don't even know how I thought of this change of variables, but here it is. I'm going to let u be equal to tz, and I'm going to let v be equal to z minus tz, which is z times 1 minus t. So the Jacobian says du dv is the absolute value of the matrix partial u with respect to z, partial v with respect to z, partial u with respect to t, and partial v with respect to t, which is absolute value matrix. Partial u with respect to z is just the t. Partial v with respect to z is 1 minus t, and that's a z, and this is a negative z. So that's absolute value of negative tz minus z plus zt. And this is why the change of variables works so nice, because that and that just go away, and we just get z dz dt. So, we now know that gamma of x times gamma of y, so we have a double integral, and I'm going to make it dt dz. That's how I'm going to integrate in that order. So our outermost integral is going to be from z equals 0 to infinity, right? And our innermost integral is going to be from t equals 0 to 1. y1 be, let's see. Well, because this, where is it? This right here is going to be greater than or equal to 0. So lower bound is going to be a zero. Oops. And if z is less than 0, then it will imply that t is greater than 1. But if this here is greater than 0, then this would mean that t has to be less than or equal to 1. And so if we take the, if we find the intersection of those, we get that t would be equal to 1. So t is 1, our upper bound of integration. Okay, so we have e to the negative zt plus z minus zt. I'm going to need to move this out. I'll just write it in later. Times zt to the x minus 1 times z times 1 minus t to the y minus 1, z dt dz. And this works out nice, because this is just, so integral 0 to infinity, integral 0 to 1, we have e to the negative z, those, we have z to the x minus 1 times t to the x minus 1 times z to the y minus 1 times 1 minus t to the y minus 1, z d z dt. Okay. Which we can turn into we can make it integral 0 to infinity e to the negative z times z to the x plus y minus 1. If I group that, yeah, x plus y minus 1 dz times the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. Yeah, it's this, and it's this z here. Because it was x plus y minus 2, but then we had this to the 1 here. Okay. All right. Now, the first of the two is just gamma, by definition, gamma of x plus y. And the second is, by definition, beta of x comma y. So we solve for beta of x comma y, and we get that beta of x comma y is gamma of x, gamma of y, over gamma of x plus y. So I wasn't lying to you. So that identity is now proven. Now we can we're close. So v sub n of 1 is v sub n minus 1 of 1 times beta of 1/2 comma n plus 1 over 2 from let's see, where was it? It was from, I did it before here, right here, when we got to this step right here. And you might want to pause the video and kind of refresh yourself on this step, but when we were here at that particular integral, the one that I've just circled, that by the definition of the beta function is beta of 1/2 comma n plus 1 over 2. Okay, so now beta of 1/2 comma n plus 1 over 2, as we just spent all the time establishing, is v sub n minus 1 of 1 times, now we can replace the beta with the gamma of 1/2 comma gamma of n plus 1 over 2 over gamma of n plus 2 over 2. Okay, now gamma of 1/2. I could spend a whole video on gamma of 1/2. That's the integral from 0 to infinity of e to the negative x, x to the negative 1/2 dx. And if we let u be equal to root x, then 2u du is dx. And so we would get that this is also the integral from 0 to infinity, and we would have a 2 out here, of e to the negative u squared du, because the this would cancel out here with the, when I replace the dx with the 2u du. So this integral right here is, it's really cool how all the different branches of the math come together here. But this integral here is, it's a, oh gosh, what's the guy's name? It's a Gaussian distribution. E to the negative u squared is a Gaussian distribution. It's not a normalized Gaussian distribution. By the way, Gaussian distribution is just a, it's just a bell curve that you're, wow, that's a bad bell, but it's just a bell curve. And when we say normalized, we just mean with area 1. So if this whole curve is some function g of x, for g for Gauss. We say that g of x is normalized when the integral from negative infinity to infinity of g of x dx is equal to 1. In other words, the area under that entire curve is just 1. And that would make sense because then it would be a probability density function, because the probability of picking something, some interval under the curve is 1. Okay. Oh, so it turns out through a very, maybe I should make a addendum video to this, maybe evaluating this integral, but it turns out that the integral itself, ignoring the factor of 2, turns out to be the square root of pi over 2. And I should probably make a video on that. And that's just, it turns out that if we were integrating from negative infinity to infinity, it turns out to just be square root of pi, but since it's an even function, the integral will just become half of that. So square root pi over 2 multiplied by the 2, we just get square root pi. That's pretty cool. So v sub n of 1 is square root pi v sub n minus 1 of 1 times gamma of n plus 1 over 2 over gamma of n plus 2 over 2. And we really could stop here, honestly. We have a recursive way of getting the formula for a n-dimensional unit sphere if we know the formula for the n-1 unit sphere. So, we know, for example, when n equals 3, it's 4/3 pi r cubed, and then we could get 4 and 5 and so on. But we can do better. We can say that v sub n of 1 is square root pi times gamma of n plus 1 over 2 over gamma of n plus 2 over 2. But now we can replace the whole thing. In other words, we can go back again, because now we can do v sub n minus 2 of 1, which is square root pi times gamma of n over 2 over gamma of n plus 1 over 2, which, if we go back again, now we can do v sub n minus 3. That's square root pi times gamma of n minus 1 over 2 over gamma of n over 2. Well, we can keep going back and go to just v sub 1, the volume of a one-dimensional sphere, which is just a line. That's square root pi times gamma of 1 over gamma of a half. And that is square root pi to the n, or multiplying n of them, times gamma of 1 over gamma of n plus, see, because this cancels, this, they're all going to cancel there. Gamma of 1 over gamma of n plus 2 over 2, which is pi to the n over 2 over gamma of 1 plus n over 2. Thus, v sub n of r, the volume of an n-dimensional sphere of fixed radius r, is pi to the n over 2 over gamma of 1 plus n over 2 times r to the n. And that is the formula for the volume of an n-dimensional hypersphere of radius r. That is it. We are done. Almost. I just want to show you that my claim at the very beginning of the video, about the volume here with the square and the circle and the cube and the sphere, and how if we increase the dimensions, the volume does indeed go to 0. Because look at this formula here. As n approaches infinity, v sub n of r, as n approaches infinity, so we were just considering unit spheres, so we can just get rid of this r to the n here, because that's always going to be 1. This is a constant, or pi to the n over 2, it's not a constant, I'm sorry. It will increase somewhat as the n approaches infinity, but this here is a factorial, and it's going to go to infinity a lot quicker than this, right? Factorial will grow quicker. And so what that tells you is that the denominator is going to get much larger than the numerator, and there's going to be some critical point, obviously. In other words, a point at which the volume becomes optimized. Like I think it's around at n equals 7, I think. In other words, if you were to keep the radius of your sphere fixed, and you could just let it be a unit sphere without loss of generality, then at what dimension would the volume of the sphere be the largest? And I think it's at n equals 7, and I think the surface area is at n equals 5. But after that n equals 7, or after that critical point, v sub n of r goes to 0. And that finally concludes my video and my claim that the sphere inside the hypercube does go to 0. And with that,